right, super. Everyone is on time. This is the first time we're starting a CSAIL event on time. Hello, everyone. My name is Daniela Rus. I'm the director of CSAIL, and I'm so delighted to welcome you and to thank you for being here with us to help us celebrate a 20-year-old cryptographic puzzle and the opening of a very special time capsule. So here's what's going to happen. Professor Ron Rivest will start with a presentation of the puzzle. And then we will hear from the teams that solve the puzzle, Bernard Fabreau and Simon Peffers and his team. And after that, we will move outside in the R&D Commons, where we will open the capsule. We will celebrate with wine and with champagne. Sorry, not wine, with champagne and cake. And we will have time to view the items in the capsule. And since the capsule was supposed to not be opened for 35 years, we're going to put the old items back in. We're going to add some new items. And Ron created another new exciting puzzle, which will supposedly take 15 years. Yes, Ron? Something like that. So please join me in welcoming Ron Rivest.
Thank you, Daniela. Great to be here. So I'm surprised at the turnout. It's nice to see all of you. It's wonderful. Thank you for coming. So it's quite an interesting story, and so we'll try to give you a brief overview of what has happened with the technology and so on today. And then there'll be actually just a day on Friday where we're going to be talking about verifiable delay functions. So those of you that might be interested in more technical detail can come hear some of the talks then. So today will be just sort of an overview, an introduction. So as Daniela said, it's a 20-year-old puzzle, and my task here is to tell you about how I created the puzzle and what it was for and significance, and then you'll hear from the solvers about that. So the puzzle design was something that predates the LCS 35th celebration. Adi Shamir and David Wagner and I worked on this puzzle back in the mid-90s. And then we had an event, the LCS35. Should we use the microphone? Okay. And the LCS35, yes, people in the other room especially. My apologies for those of you, and also those live streaming. I usually wear a lapel mic, which I'm used to, so whatever. Anyway, so then we had an event celebrating the 35th anniversary of the Laboratory for Computer Science in 1999, and that was quite a bash. And I'll tell you a little bit about that. And as part of that event, we created the time capsule, and associated with that time capsule was a cryptographic puzzle, and I'll talk about that. And that's what was solved, and that's why we're opening the time capsule today. So here's the essence of the puzzle. Can two women have a baby in 4.5 months? Right? So some things are intrinsically sequential, right? I mean, having a baby takes 9 months. You can't short circuit by having two women working on it together, right? And so there's computations that are, we think, intrinsically sequential as well. And so that's the essence of the puzzle. Can we design an intrinsically sequential computation that's going to take a certain amount of time to compute the answer? So these are computations that can't be sped up using parallelism, and they require a predictable amount of operations in terms of how many you have to do in a row. So you start off at some start position, and then you go step by step through the puzzle, following your nose, unrolling the string, whatever the metaphor is you want to have, until you get to the finish, and that's it. And there's no way to short circuit this and jump around and skip some of the steps, get there done fast. You just have to do it one after the other. So that's the idea of an intrinsically sequential puzzle. To realize that, David Wagner, Adi Shamir, and I worked on the following design. I'll give you some math here now, so a few equations. If you don't do math, you can just go to sleep for a slide. So we created N as the product of the celebration. We would go another 35 years and have the bag open then, or as close as you can get with this cryptographic puzzle idea. So that was the proposal, that I design a cryptographic puzzle that would signal the opening of this bag. So when that puzzle gets solved, then the bag gets opened, basically. So that was my challenge, was to come up with a puzzle that would take 35 years to solve, exactly, if possible. Of course, I'm a theoretician, and being within a factor of 2 is good enough for me usually. But how do you create a 35-year puzzle? So I had to choose parameters n and t for this thing. The modulus n was easy. That was a product of two 1024-bit primes. But t is the one that sets the difficulty, really, and the question is how big to make that. So I could measure how many squarings I could do a sec. Yeah, there was some computations we did in Java, and there's also the one that, yeah. So yeah, there was a number of ways we tried to benchmark what we could do in 1999 in terms of squarings per second. That's the key factor, of course, right? How many squarings, how many steps can you take per second with the technology available at the time? And we estimated that with good technology at the time, and we had some estimates from Java that we scaled up and some other things that we scaled up too, that 3,000 squarings a second would be about what we could do then. However, this is a 35-year puzzle, and Moore's law was still alive and well and kicking at the time, right? And so we have to have some sort of model for Moore's law and its progression. So looking at the National Semiconductor Roadmap and talking to colleagues, we figured that the following model would be about right. Estimate that it would run 22% faster every year for the next so many years, 13 years, until 2012. And then Moore's law would sort of die or fold a bit. It would slow down a lot. And from 2012 on, it would only grow, the speed would only increase at 7.5% a year. That was our model for Moore's law. It's not a perfect model, and you can argue with that in lots of ways. So that gave a factor of 65 total improvement in speed over the time period of the puzzle. That was our guess as to what it would take. Using that guess, we could then compute a value of t. I said, well, the first year you should expect to do 95 billion squarings, and then it increases by 22% a year after that. And if we set t to be 79,685,186,856,218, which was the number we picked, which is about 80 trillion, then this should take 35 years. And so that was the number of the puzzle. We picked that based on our assumptions of Moore's law. So that was put there, and then it's like, Sleeping Beauty or something. They just sort of fell asleep, and nobody paid attention to this much for quite a while. We closed up the time capsule too. Here's Bill Gates putting a version of Altair Basic into the time capsule. And so that's one of the things we should be pulling out shortly, along with about 50 other things, right? There's a whole bunch of stuff in there. We'll have to see what all is in there. So that was loaded. And then, as I said, like Sleeping Beauty, things just sat there and people were forgetting about it. And what is this bag sitting in the lobby of the status center, and who cares about this puzzle anymore anyway? And then all of a sudden we had a solution. So Bernard Fabreau, who's sitting here, solved the puzzle 15 years early on his home. Wonderful solutions to the puzzle. And I want to give you guys the awards you've earned and deserved, besides the recognition for this wonderful achievement. So Bernard, let me start with you. So here's a puzzle. Says this award is presented to Bernard Fabreau for solving the LCS35 crypto puzzle, and it gives the date.
Great.
Congratulations.
Thanks a lot. I should open it now?
If you want to. It's a puzzle.
Oh,
It's a
no more puzzles.
It is a puzzle. It's a little sphere you can do. Take a seat.
Okay, that's very nice.
Yeah, so I warn you, it's not easy.
Okay. Well,
Although I'm bad at predicting these things.
thanks a lot. Thanks a lot. Thanks a lot.
Okay.
It's great.
Congratulations. And we have similar awards for the other team. There's 4 of them here. So Simon, why don't you come on up first? Congratulations to you. I want to get the whole team up here. Simon Beffers from Supranational. Erwin Ausberg. Justin Drake. And Jeremy Johnson. There you go. Congratulations.
Thank you.
Congratulations. 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 So you guys did a wonderful job too, astonishing all of us with your speedy solution. You can have a contest as to who can solve this one first. But congratulations. And Simon will talk shortly then about how they approach the problem too. So I'll stop here. The following agenda is Daniela indicated, after the talks, we'll have one by Bernard and then one by Simon. We'll have a break with some food and some drink and cake, and then we'll have the opening of the time capsule. And I want to thank Laura Lynn Smith, who's back here somewhere helping with the organization, and Chachi Garcia for their help. And I think we should be doing the following last thing for all the talks we give. When people fly on airplanes, we should say that you've done a carbon offset. So that we got a carbon offset because Bernard came over from Spain actually, and Erdős from Turkey. So we've carbon offset their travel. Besides, we're paying for their travel. So that too. So climate change is so important these days. If you're flying, do some carbon offset. So that's the event for today. So Bernard, you're on next, and we'll set you up here with your laptop. Yeah.
You've been faster than expected. So how many times do I have?
Okay.
More or less, just to see.
Okay. So let me just play by ear, however you like.
Okay.
We're flexible here.
Okay.
So while you get us up, so it was quite a shock to me to see this letter saying he'd solved the puzzle, because I had no idea that anybody was working on this at all. And so to get the email forwarded from Daniela saying that the puzzle's been solved, and then he provided the message that was proof that the puzzle had been solved. So there's no doubt. We did confirm that, did the computations and the checking. So it was great to see. And this stuff is the fact that it came out a bit early. You're all set?
It's not coming.
Did you plug it in?
Yeah. Oh, maybe it's not the correct one. Okay. Oh, good job.
Yeah, there's two.
My bad. Yeah. Right. Okay.
Maybe we'll hear more about the difficulties of predicting technology advance in Moore's Law Tier 2. But Bernard, the show is yours.
Whoa, wait.
You're on?
Right.
Okay.
2 seconds. Okay. So it's not my computer, and I didn't actually do the presentation. My brother did it. I've never spoken like this in public, so please indulge. Why is it in autoplay? What's that? Yeah, okay. Okay, let's go. So, well, thanks a lot for everything. I'll thank people on the last slide. So there's this time capsule, and inside it there are artifacts related to many different things created by people involved with the MIT one way or another. There's, for example, a paper called Spreadsheet. It was called simply Spreadsheet because back then spreadsheet didn't exist, so you could create a paper and call it Spreadsheet. And so that's turned out that became later on VisiCalc, the first spreadsheet. So I don't know exactly when that would be, like late 70s. The paper was 79. The paper, yeah. VisiCalc, I don't know exactly, but 79, the paper, yeah. And here is a video game, Zork, one of the first, not the first, but one of the first video game. And it was also late 70s on the PDP-10. This is not a PDP-10, but whatever, it's a picture. So back then, it was a very pixel world with big pixel and monochrome screens or a few colors. And so my brother, who did the presentation for me, picked this theme for the presentation. So it's going to be, I asked if Ron agreed, and he said it's okay. You can so, okay, my name is Bernard Fabreau. I just put my email there, so it's easy if someone wants to email me, okay? And I explained the first solution. The first solution. So basically, the timeline in 1999, so the problem was created, the parameters were set. We'll see later on, that's very exciting. I've got numbers because I got people to run actual computation of the library I used on 1999 hardware using 1999 version of the library I used. So that's going to be very interesting because the parameters are basically very good. So yeah, you see, there's not going to be many slides because at this speed, next slide, we're done. So 2012 is an important date because in the paper, there's a prediction about 10 gigahertz clock rates. And I saw basically Ron Rivers didn't get contacted by anyone, I think, about the puzzle for 20 years. But people talked about it online. There were forums where people talked about it, a website, there were tweets about it, question on the Stack Exchange. I mean, it was mentioned, and everybody was commenting basically the same. Everybody was commenting, that estimate is way off, computer didn't reach 10 gigahertz, so is it possible? Nobody's ever going to solve this. So So that's important because back then, if you had a top-of-the-line Intel CPUs, you could reach 4 gigahertz without overclocking. So that's when I read it, I thought, okay, that's not too bad, right? 10, 4, okay. So we'll see next slide. So 2014, something happens. Credit was you because there are many Intel engineers here, and they actually know him. One guy posted code on GitHub. John Leslie Hurd, I emailed him, he couldn't come. And he posted code on GitHub. He said he wanted to configure FPGA to solve the puzzle, but he didn't do it. But he had the idea, so that's the code is on GitHub. It's posted, I think, Simon told me it's apparently auto-generated code. I don't know, we don't know exactly how he did what he was doing, but the idea was there, the puzzle was mentioned. So, I mean, really several people mentioned it, so it's not as if it was totally Sleeping Beauty. It's just that I think people read about it and just thought, yeah, it's not solvable using a regular PC or regular computer. So late 2014, I discovered the puzzle. I thought it was already 2015, but people found all message of mine on forums and reminded me that it was late 2014. So, and really what I did is I wasn't blocked by the fact that gigahertz, I mean, we didn't reach 10 gigahertz, that clock speed didn't reach that speed. Because I thought it was quite close, actually, really, I thought it was quite close. And so I did a quick computation in my head. I took the estimates times 13 until 2012, so from 3,000 square rings, 39,000 square rings, and then 2 more years at 7% each year, so about 50K square rings per second, more or less. Really, it was really ballpark. And so what I did is I took the 4 gigahertz clock speed, so 4 billion cycles per second, and I say okay, and I divide that by the estimate, and so I did like a quick mental computation, and I say okay, that's 80,000 cycles per step, and okay, these are big numbers, but really I thought there's no way computers are that slow today. I saw that number and I say 80,000 cycles. You don't need 80,000 cycles to do one iteration, even if it's big numbers. You don't need that much. I mean, it's not that. I mean, the computation is not that complicated. So what do? You test. So I tested with Java first, and with Java, it's very interesting because I got basically an estimate very close to estimate in the puzzle. And I saw once I found a solution, I saw people doing the same with Python code. Like I think default Python. I don't know if their code is correct, but the same thing. They are like 40 years needed to solve the puzzle, something like that. So I mean, it was interesting. So they said, okay, in the puzzle it's correct. What I simply did is I used a library optimized to do big integer manipulation. And so the first result I got on my Core i5 CPU was more than 11 times faster than the projected estimate. I mean, and I knew it would be faster. I didn't know if it would be 5 times faster or 20 times faster, but I knew it would be faster. And so, but that would still amount to about 4 years and 5 months of uninterrupted computation. So that was still a bit too long. So I wasn't that motivated to start yet, but it motivated me to buy a faster CPU. So yeah. So, but I procrastinated a bit and did a few research, and so okay. And so I bought. Oh yeah. And so okay. So well, basically the code is really deceptively simple. I'm no cryptographer. I don't invent algorithms. But yeah. And then so I use the algorithms you people invent to have them run on the CPUs you chip engineers make. So that's what I do, right? And so the code that's really like, and it's probably not even idiomatic C code because I hadn't written a line of C code in 20 years. But yeah. So and I did it wrong, actually. No, the code is correct, and it's fast enough. But it's not the fastest because I tried with GMP to do the mul and the mod in one instruction, which GMP offers. And for whatever reason, I made a mistake, or it's because the hardware was different, I don't know. And I thought that for squaring, it was faster to do it this way. Apparently, I made a little mistake, so it took a bit longer than expected. So using my new bugged CPU, in 2015, I was reaching, basically 750,000 square rings per second. So that was much faster than than what the puzzle estimated. So by the end of 2015, I was at 15% done. I have a few timestamps left in the file saved on the computer, so that's why I could find exactly where I was. At the end of 2016, 48% done. 2017, I reached 66% of the computation at the end of 2017, but something interesting happens. Someone on an article about LCS35 mentions in a comment that on his own Core i7, he could have the solution in 4 years. So he said, if I were to start now, I would have the solution in 2021. And it's interesting because the next two comments, like people just don't believe him. And but he didn't start. By then, I had a big head start. I don't know if he actually started. I don't think so. I hope not. And yeah, so that was very interesting because he noticed it. So. By the end of 2018, I'm at 91%. So the computation was running on my everyday workstation because so it was easy to keep an eye on it. You cannot really parallelize it on a regular computer like massively. So I had only one core running basically. And so because these CPUs are nowadays so powerful, I couldn't even feel that it was running on one core full time because I had 3 other cores left for everything: coding, compiling, processing the web. Well, it's a workstation, so I don't really. But what else? Yeah, sometimes even running full blockchain nodes. I mean, on the same computer, it's just crazy. And meanwhile, it was just happily cranking towards the solution. So basically, I just found it and just let it run and say, why not just let my computer on at night instead of shutting it down? So yeah, so that was every 1 billion iteration I would save a file. I didn't bother with a database or files on the file system. It's a perfectly fine database. And so I would say that every 1 billion iteration I would save a file because then I wouldn't end up with too many files. That was like 79,000 files. And so we can see here, yeah, the progress. And so, yeah, so sometimes I had to relaunch the computation because basically it's interesting. I relaunched it exactly 50 times. So over the course of the computation took 3 years and 3 months, but over the course of 4 years. And so basically about once per month, it was relaunched because power outage, I moved country, I was on vacation. I mean, there were many reasons which made, yeah. And sometimes I would wait a bit before restarting computation. So hopefully I didn't waste too much time because I still wasted like 7 months, something like that. So it's crazy. And at the end, when we were near the end, so that one like on April 12, actually I wasn't at home. I was on the road with my brother, and so and we were discussing about it in the car. So we say, okay, by now when I get back home, we'll see if we have the solution or not. So and that's what one file would look like. So it just like the number, and from that number you can restart at any step. So I would just make sure, of course, to back up these in case in case something happened to the hard drive, right? I mean, so I would do backup of this like everywhere. So yeah, remote server, USB sticks, other computer at home. Everything. Email, everything. And so April 15, I find a solution. I do a silly little dance in front of them. And I wait a bit. I'm so happy to have. I'll show it later, the solution. But I emailed the next day. Oh yeah, and so that's really great. So Ron Rivers talked about it. But basically, the press release was supposed to be the CSAIL press release was supposed to be on the 26th, and I have to thank my brother who's here a lot and. And Kevin Zhang and all the guys at Npool because they did a surprise. We tried to time it with the CSAIL press release, but basically in that BTC block, there's a header saying congrats Bernard for solving LCS35, but it's not in a transaction. It's in a block header. It's in the Coinbase data for the blockchain folks here. Yeah, I see some are. So that requires a cooperation from a mining pool because it's impossible to do it solo nowadays. So that's huge. It's in the blockchain. And sadly, the press release got pushed back 4 days. But yeah, it was with the Chinese guy. So there was a little bit of miscommunication. But thanks a lot to my brother, to Npool. Yeah, that's so. Okay, so a very nice modern graph. So 79 trillion squarings. Thankfully, these are, I don't know, these are American and current British English trillion and not French trillion. Otherwise, that was like 1 million times more difficult, right? And none of us would be here. So 2015, when I start, the estimation, cumulative computation, if it had been done from the start, would be at 12.5%, and basically a straight line. So in 2019, when the solution is found, the cumulative computation from 1999 using the parameters in the puzzle would be at 25%. Okay, so and you can see that the estimate more or less for 2034 would be nearly 200,000 squaring per second. On my PC, I could reach a little bit more than that because I made a mistake. I told you I could reach like 800 and something. And Simon tried it on a latest gen Core i9 or Simon Origin, I don't know, and he got nearly like 1 million squaring per second on a regular PC. So that's faster. Yeah, that's the difference with the estimates. And it's of course in 2000. I mean, it's now, and so that makes a big difference because in the original estimate, most of the work would be done at the end. If that makes sense. Okay, so that's great. So some real numbers. So the estimation is not entirely clear. I don't understand if Java was used back then because there was an email which Ron forwarded us from Scott Contini from RSA back then, who estimated 3,400 squaring per second on the top of the end 1999 hardware, and Ron lowered it a bit to 3,000. So thanks. So that's nice. And I actually got the GMP guys, and I have to thank the authors and maintainers of the GMP library because not only they wrote this fast library, but they also found out old hardware to try on the hardware which was top of the line in 1999, the version of GMP from 1999. And so they got 3,800 squaring per second. So that's very interesting because it's very, very close from the parameter that was chosen. But they also tried the latest GMP version, so it's purely software, on the exact same hardware from 1999, and it's 10,500 squaring per second. So that's 2.7 times faster than what GMP would do, what the old GMP version would do. So the advance in software could be seen here. It's already like really huge. And at one point they stopped optimizing for 32-bit architectures because basically we all moved to 64-bit CPUs. So they're pretty sure, they told me they're pretty sure if they had continued to optimize for 32 bits, they would have another 25% gain. That's an estimate. These are real numbers. The 25% is an estimate, but I think it's close. These guys know what they're talking about. So on a 32-bit computer in 2003, we were at 37 squaring per second. So thanks a lot to the guys in the because you have to find people with this machine still running. So I went to IRC, to the Slackware channel, people running on Linux distribution. I mean, it's still current, but it's existing for a long time. So it's quite fast. And so in the numbering, in my number, that's the number I actually got. So that's basically a 13 times speed up compared to the estimate, something like that. So this compensated for the fact that we didn't reach 10 gigahertz clock speed, right? It more than compensated for it. Like there are huge speed ups, and as I said earlier, it's because most of the computation would be done by the end. Finding that like in 2014, 2015 is nearly like cheating because you have these amazing CPUs and you just write 2 instructions and a loop and save files and use a fast library. That's all I did. So the message. Oh yeah, that's cool. So when I found the message at first, because my numbers were wrapped, and I could only see the beginning of the secret is identical to the number in the puzzle, and so I thought there was a big mistake. I was like, it's not possible. It's the same number. Like I was like, there's a huge mistake. Like Ron encoded the 0 there when I XORed the 2. So and then I saw the end that the end they were differing. And so I said, okay, I've got the answer. I didn't do the XOR and the ASCII thing yet, but at that point when I saw that, I say, okay, that's good. I have the answer. That's so good. It's gonna be a short message. And so happy anniversary LCS. there it says it's not the exact message. It says seed value B is the message a tiny bit different. Basically, it gives you this B, and so am I okay? Yeah, I think I'm okay because it's nearly done. So so yeah, here's some fake closure code I did for the slides. So I should have used scheme. It says that just below a prime with B you compute that. So mod power 5 to the exponent B, and then mod 2 blah, 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 blah. And we've got this number. We have to take just below prime factor. That's a nice int. So you just use next probable primes. That's closure just calling Java here. And so indeed it was pretty close. And you see just the n. So the prime was pretty close. You divide n by the first prime. You have the second prime. And I certainly did something silly, trying if I had n, and that was it. So puzzle is a little bit of a game. A game has a high score. And then it was written a high score. I don't know, like high score, like this in many games. And that's the high score we reach. We all reached that. That's it. So I want to thank everybody here. Ron first for creating this puzzle, all the people involved in it, because there is a huge list of acknowledgement in the puzzles. The director, Daniel Harris, and all the CSAIL. Yesterday, my day here was just amazing. First, Ron showed me around the building, and then everybody's been super nice. I don't know, Cree, I don't know if she's here. She took care of me for like 1 hour. Yeah, it was amazing. Of course, Simon original the second team, because we exchanged a lot of email IDs for the slides and discussed about many things. I was like more excited by their solution than mine. All the GMP authors and maintainers, of course, because they've been so nice. The Stack channel, I mentioned that. Mercin Forum, which came up with a little benchmark. I had the guys from GMP and Run. FactorDB, but we won't have the name. So Marcus from FactorDB.com, because the thing is, it's not that much of Sleeping Beauty. It's a website where they where they store factors of numbers of interest, and from that puzzle was posted there. And I asked him, but there are the problems. They lost the timestamps. They know it was before April 2018. I certainly didn't post it there, but the number is there. It's waiting for the factorization, so I'll post it later on today, unless someone want to have fun from the slides doing OCR or whatever. But I'll probably be filling in the factors. Everybody at the Hacker News community, because we had several hours of fun when the announcement was made. It was front page for many years. It was lots of fun. Npool, I told it like Npool. Thanks a lot for that. They could make that Dynablock header. Friends and family who are here. Amit Niranjan, Matthias, who I just met. Hi, Matthias, who's there. My little doctor, of course. My partner, Catherine, who's there. And last but not least, my old trusty CPU, which I can say it. I can say it. Yeah. I had to dismantle my workstation, and so I gave him a nickname, and I fear it's going in the new capsule. So long, and thanks for all the squarings.
Wonderful. Thank you very much for that explanation. I hadn't heard so many details yet in our discussion, so that was great to hear. So next we'll hear from Simon Peffers, who was part of the team that found the second solution just days after the first solution was found. And he'll talk about his approach based on FPGAs, somewhat different computational model, and what got you motivated. And these guys didn't know about each other. I was amazed when I got the second email. I said, Simon was surprised to hear about the first one. So.
Let's see if I can get this to show up on there.
There you go.
Okay, good. Yeah, so I'm Simon Peffers. I'm at Supernational, and I'll tell you a little bit about how we turned 35 years into 2 months. So who are we? So I actually represent, this is a collaborative effort here, and we call our solution CryptoPhage, so you can see that there. You can also go to cryptophage.com and learn lots more about it if you want to. But this is a collaboration, as Ron said earlier, between Ethereum Foundation, Protocol Labs, Sabanci University, and Supranational. And the goal of this collaboration wasn't really to solve this time lock puzzle, although that's a pretty good thing to collaborate about. But it's really to go after this VDF function, this verifiable delay function, which is a new cryptographic primitive. And all it is, it turns out, is basically a time lock puzzle with a V in front of it. So that V is really the verifiable part, which allows you to sort of generate a proof and quickly verify that you did that whole long computation that took maybe 3 years or 2 months, whatever it is. And as we started working toward this VDF, and one of the things it requires is sort of custom hardware. For a VDF to be effective and practical, it has to be fast, meaning that you can't have other people run it faster than you can, which ultimately means our goal is to build an ASIC. But as we started working toward it, we had some initial research that said we could do it pretty fast on an FPGA. And we thought this time lock puzzle would be a great opportunity to go try out our hardware, see what it could do, and crack a cool puzzle. So that's what we've done. Ultimately, I'll say the goal of this collaboration is to make VDFs generally available as a public good. So we're going to be open sourcing the code from our solution in the coming days. You can go on GitHub and find it. I hope you do. Take a look, and if you want to improve on it, that'd be awesome. Send us ideas. I also want to mention that Juan Pineda, who's also working on VDFs, is here in the audience. And he has yet another solution going. This will be the third one on an FPGA, and I think it's due to solve on June 5th? Yes. 21 days from now. So there's lots going on. And then I'll say, too, on May 17th, there's a VDF day. Ron mentioned it. But Erdinch, who's my collaborator here, will be presenting our custom multiplier circuit in gory detail, so you can come learn all about that if you want to as well. So Bernard talked about this a little bit, but I just wanted to walk through sort of how you speed up this kind of a computation and break that down as to how we got to this 2 months. So if you step back, there's kind of 4 ways you can speed up computations on a computer. You can turn up the clock speed, but as we saw, that's been pretty stable for a decade or more at 3 to 4 gigahertz. So that wasn't a good lever for us. You can parallelize computations. So if you can have a problem, you can split into many small pieces. You can send it out to many cores and do it in parallel. That also doesn't work because Ron created a problem that is inherently sequential. And so the kind of third and fourth options are to build sort of new computing primitives. Rather than what you might find in a CPU, you can put other things in there that might do this particular function better or faster. And then the fourth one is, if you've got these sort of computational primitives, how do you use them as efficiently as possible and not let them sit idle? And so if we walk through this sort of chart, and this isn't meant to be complete or precise, it gives you kind of an illustration of the major events that sort of led up to this. But as Bernard said, you've got the 32 to 64-bit multipliers. It gives you about 4x. There you're getting sort of bigger multipliers inside the CPU. And then you've got some new instructions that came out in x86, and in fact, Erdinch contributed to some of those earlier in his career. He's been working on multipliers for a long time, it turns out. And those basically modified the way dependencies work inside of the processor. So as you do the carry chains in doing this big integer math, it relieves some of those dependencies, and that goes toward allowing you to use the existing resources more efficiently. So in a superscalar design, right, you can fill that pipeline better and keep those execution units going. And then the next one is these sort of, and that's probably another 3x or so. And then the next one is this sort of algorithmic improvement. So as you go to different libraries like libgmp, which Bernard used, incorporated all of these things in it, and they really optimized the software to make sure it's filling those execution units as much as it can. So it's being efficient about that computation. And so that's how you kind of get to Bernard's, his solution at 3 years plus, that kind of a time frame. So what we did is just take that further with the we used an FPGA, which I'll show you. And the FPGA lets you design new primitives, right? So we designed basically a customized multiplier that Erdinch sort of created, which is specifically designed to do low latency mod squaring. It really is a multiplier that's designed for this puzzle. And we used two 512-bit multipliers instead of 64 bits. And we have a customized reduction function, which is that modulo function. So we can do that very fast because in the end, what we have is hardware that can only perform this function, but it does it really well. And then finally, because it's only doing this function, we can really use those resources as efficiently as possible, so we can keep them busy because we can precisely schedule the data through those functional units. And so that got us in the end to about 2 months. And I'll show you the device. I actually brought this guy in here too. so you can see what it looks like. So here's the FPGA, right? And it looks kind of like a large graphics card. It sits in your computer. There's a big chip under this heatsink, and it ran away. So fortunately, that worked pretty well for us. So you can see here, right? So we use this FPGA. Ours is from Xilinx. There's others out there. What an FPGA is, it stands for Field Programmable Gate Array. And you can think of it as it's this chip with a bunch of circuit building blocks. It's got various core components. And you can configure it to do whatever function you want. So it's more specific than a CPU. It isn't general purpose anymore. You have to really program it. But it's not as optimized as a custom ASIC would be. It's somewhere in the middle. But the nice thing is that you can get going very quickly with it. So what we did is, initially we started on AWS F1, which is a cloud computing platform where you can rent FPGAs. And this guy costs about $8,000 and takes weeks to ship. On F1, you can get going in minutes, and for a couple of dollars, an hour. And that let us get going once we sort of found the puzzle very quickly, writing RTL, which is a specialized language for describing circuits. We could write that and start building this multiplier and testing it, and getting it going on the FPGA. There's a fairly long process once you write the RTL. Unlike Bernard's code, which I'm guessing compiled in seconds, it takes about 12 hours to go through a synthesis. So every iteration took quite a while. But when we got it working then, right, it runs very fast. So we initially started running actually in AWS, and we ran for a while there. And as we sort of optimized the design further, we needed sort of more of the resources of that FPGA to get down to that 66 nanoseconds, which is where we ended up. And we eventually bought an FPGA, this guy, which gives us the full metal. In a cloud kind of environment, right, like this, they lock off some of the parts of the FPGA for management logic and control, so you can't use the full thing. So we ended up starting it there, finishing it there, at about 15 million squares per second that amounts to. The other interesting thing is, so as these guys pointed out, you're going to do these 79 trillion iterations, squaring every time. What happens if you make a mistake along the way? The last thing you want is to wait 3 years or even 2 months, and you get to the end and it's not the right answer. So we incorporated a lot of checking along the way in our solution. So on the FPGA, every 50 million iterations, we pull off that intermediate value. And that, in the end, those intermediate values are parallelizable, so it's one ways we could speed it up. So in the end, we were able to check it by sending those onto regular computers, and we used, cloud, there's plentiful processors for rent, so we just sent every intermediate in and could check it on a computer there and make sure the answer was the correct one. The other thing we did is some fancy cryptographic functions, which I don't really understand either. I'm more of a hardware guy, but we were able to pull out those intermediates and calculate the V part of the VDF, the proof, and also prove that way that it was actually generating the right answer. So in the end, happily enough, on May 15th at 10:22, the final iteration happened, and it spit out this number, and we were able. May 10, and decode the answer, and it worked. So we were very happy about that. In the end, I think this was a very fun problem. We had a lot of fun working on it. I think as we go forward in VDFs, there's probably a couple of years of work to do there to really build up the hardware and the software necessary. And we're really looking to collaborate with people in the community. It's going to be open source as much as possible. And if anybody's interested in working on VDFs, either the hardware side or software side, I'm sure we would love to have help. The various blockchains would love to have help, so please reach out. And thanks.
Thank you, Bernard and Simon, for those wonderful presentations and for solving the puzzle twice. So I guess we break now for, pardon? Oh, Q&A. I was just thinking we could do Q&A. Yeah, we do Q&A. Q&A, questions for the solvers. There's one.
Just tell you one, but when you got the email with the answer, did you remember what was the message that you had sent?
No, I didn't need to. Because the message was self-verifying. The message contained the seed for the factorization. So, I mean, people send me things all the time. I get emails saying I solved how to factor big numbers. And I say, okay, factor this. And you don't need to know what the factors are, right? This is sort of like that. They're self-verifying, right? So in fact, the next puzzle, which is going out shortly, has a similar character. It's got a product of 2 primes in it, and I've already forgotten the primes. Next question.
Can you account for idle time in your estimate of 35 years?
Idle time.
That people will not be working on it for...
No. It was a very sloppy estimate, as you can see. Yeah, good, thank you. The question is whether I accounted for idle time in the computation. The answer is no. Yeah, so.
So how are you doing the estimate this time?
That's a good question. So there's no Moore's law anymore to pay attention to. I think the estimate has more to do with how much money people are going to invest in building ASICs, right? And so it's a technology prediction is more than a thing. And so I'm trusting these guys to give me some guidance as to how important this problem is for blockchains and things like that, and how much work will go into building things too. I also scaled the size of the number up from 2048 to 3072, thinking maybe that would make it a bit more challenging for them. But you know, it's a guess. I mean, this comes down to about what is it? It's like 6 nanoseconds per square modular squaring for the new challenge. So which is you know, and Simon was getting 66 on the FPGA, so it was a factor of 10 faster than what we're doing with the FPGA. We'll see how good this is. Again, I'm a theoretician, you know, a factor of 2 either way. You know, I don't know. So we're setting it up. So the next puzzle, if it gets solved before the second 35th anniversary, 2034, I guess we'll open it again. But I tried to make it a little harder this time. So I suspect that we'll get to the 2034 and it won't be solved yet. And the director of CSAIL at that time, if there is a CSAIL, we'll have the opportunity to open it at that point. So, yeah. Any other questions?
Questions for Bernard or Simon?
Yeah.
Or the team?
Karen?
What are you guys going to do next?
No, I'm just gonna solve this one. No, and yeah, life as usual. I mean, I don't think I'm gonna try to solve the next one, but who knows? I mean, there are milestones, so maybe just to see which milestone could be reached just by a software solution. Except this time I would do it correct and fast, but faster. But yeah.
That shouldn't take you 35 years either.
Guys?
Simon, did you want to answer the question too?
Sure. So, I mean, as I said, we don't have any, I don't know, maybe we'll work on this puzzle if we build, depending on where we go with VDS. But the main thing, I think, is to start building this VDF environment up and work toward that for us, and that we're very excited about doing that. Yeah. What else?
Are there any other factors?
Maybe Justin,
One more.
maybe Justin wanted to say something too. Part of the team for the
Yeah, I just wanted to plug in a few bits and pieces regarding next steps. So we want to build this VDF ASIC, which is as fast as possible, and part of that is crowdsourcing intelligent